All right. The third talk will be given by Aditya Anand from IIT Bombay. He'll be talking about combining static analysis and speculation. Aditya.
Good morning. Good afternoon, everyone. My name is Aditya Anand. I'm a PhD scholar at IIT Bombay. I'm going to talk about our work, CoSSJIT, combining static analysis and speculation in JIT compilers. This work was done in collaboration with IIT Bombay and IBM Canada. As most of you here might be aware that JIT compilers often tends to do imprecise analysis due to its budget. So some of the recent works try to do static plus dynamic analysis where they offload the costly but precise analysis to the static time. The idea is that you offload the analysis ahead of time and then use the results to perform more optimizations. We had a work at last year at PLDI where we talked about how do we optimize object allocation in case of Java. We looked into the optimization called as stack allocation, where we allocate method local objects on the stack frame of its allocating method rather than on heap. The idea was to offload the precise escape analysis to static time and then optimistically use those results to perform stack allocation at runtime. Note the keyword optimistic, as there are dynamic features offered by the language or the runtime, such as dynamic class loading or hot code replacement, which can change your code and can invalidate your static analysis results. To ensure functional correctness, we made sure we had some runtime checks. So we included some efficient runtime checks to determine whether the static analysis results which we are using are currently corresponding to the runtime environment or not. If not, in that case, we use the idea of dynamic heapification. So this was one of the first approach to soundly and efficiently use offline or static analysis results in a JIT compiler. Having this background of using static analysis result for improving the runtime optimization, let's look at some of the cases where a JIT compiler can do better compared to just relying completely on a static analysis. For example, JITs, the VM maintains various profiling information, ranging from basic invocation counts, loop invariant values, branching information, instance of checks. It also maintains dynamic class hierarchy, which talks about which all loaded subclasses for a particular class is present. It also maintains inlining table, which gives you information of list of methods that got inlined at a particular call site. With all this information, JIT is able to do pretty standard speculative optimization. Why I say pretty standard? Because when you do speculative optimization, you need a fallback. And in most of the scenarios, the fallback is often discarding the generated binary and falling back to interpreter. Now for the object allocation optimization, since we have an efficient fallback, which I just mentioned, is heapification. How can we get the best of the static analysis and runtime information? Can we make JIT compiler go more aggressive in terms of performing stack allocation? And that's where this work comes into picture. The idea is we will, instead of generating conservative results statically, we will enrich the static analysis with possibility of speculation at runtime. And then we enable the JIT compiler to perform speculative optimization based on the static analysis result. Let's briefly look at some of the cases where we try to enrich the static analysis. The first case is about the way we handle invocation statement is regarding polymorphic call sites. Consider this code example. We have three classes, class A, class B and class C, where class B and class C are extending from class A and overriding the method bar. At line 14, we have a polymorphic call, and based on the receiver type, the corresponding bar method will get called at runtime. If you notice in class C, the bar method in class C, at line 22, we are storing the parameter into a static field, the global, which is global, and which makes the parameter that is being passed go out of the scope of the allocating method. So while doing standard static analysis, the generated result for method foo will take meat at this call site, and it will take a meat for both the callees and generate escaping for the passed argument. Here the passed argument was 05 and a field reachable from 05 is 07. So standard static analysis will give escaping for both of this object. Now it might happen that at runtime the dynamic class hierarchy table shows that the class C is not loaded itself, which means that the reason why we were marking the object as escaping is not present itself. So we can go ahead and still can do stack allocation. Even if class C is, let's say class C was present, and the runtime profile shows that class B is taken most number of the time, and hence we can still do stack allocation in most number of the cases. And to encode this information in static analysis, we generate this kind of additional conditions. So we call it as polymorphic conditions, where we say that at line 14, if the receiver object Z type is B, you can go ahead and allocate object O5 and O7 for on stack. That's what we do. The second condition is about the way we handle control flow. So similar to the previous case, now let's see if an object is escaping in one of the conditionals. Let's say in the else branch here, the object is marked for escaping. Similar to the previous case, again the standard static analysis will take a conservative approach and mark object O6 as escaping. Now to again encode this information, that it might happen that at runtime the other branch is taken most number of times, we add an extra condition for branching, where we say that if this is the branch which is taken most number of the time, you can go ahead and mark it for stack allocation. The third case is regarding the way method inlining is handled. So static analysis doesn't consider the possibility of method inlining at runtime. Now consider this code example where we have a method bar in class B, and at line 13 we are creating a new object and storing into parameters field. This object is escaping just because it's being stored into parameters field, and standard static analysis will mark O13 as escaping. It might happen at runtime this gets inlined at various call sites. Here it can get inlined at line 4. So what will happen is, right now in method bar the object O13 was on heap, and if bar gets inlined in method foo, O13 becomes local to method foo, and now if foo is not making O13 escaping, you can allocate this O13 on the stack frame of method foo. To have this encoding again, we generate additional condition saying that at line 4, if the method b dot bar gets inlined, you can mark O13 for stack allocation in method foo. This way we allow some of the callee objects also getting stack allocated on caller's stack frame. To summarize, now for our static analysis, along with direct stack allocation results, we also generate these conditional stack allocation results for different cases. And once we have these results, we pass this information to the JIT compiler. In the JIT, we basically bring out all the profiling information as well as like class hierarchy table, dynamic class hierarchy table, profiling information, and we use this the conditions which we generated statically to get the final outcome. So we have left some holes which can be resolved at runtime to get better results. The algorithm, the in detail algorithm is present in the paper. You can have a look at it. Our evaluation is, our implementation is done in like the static analysis is done in suite framework, and the runtime component is present in OpenJ9VM. We used benchmarks from Decapo newer as well as older benchmarks. We also used SpecJVM benchmarks. We had two schemes, the baseline scheme where we use the existing escape analysis which is present in the JIT compiler as the baseline, and then the CoSSJIT approach which uses direct as well as conditional scheme. Let's look at the enhancement in the stack allocation. So here we have both these schemes present, the baseline as well as the CoSSJIT. And if you look at some of the benchmarks, let's say graph G, you see the static count goes from 12 to 109. This represents the number of allocation sites that were marked for stack allocation. Similarly, the dynamic count, which were the actual number of objects that got stack allocated, improved from 5.2% to 14.2%. Similarly, this number of stack bytes that actually got stack allocated also improved from roughly 8.3 GB to 20 GB. As we were using speculative optimization, we saw some heapifications happening when our speculation were going wrong. On an average, we saw an improvement of 1.4 times in stack allocation, and then on improvement of 5.7 times in stack bytes. This means that this much of less heap memory we allocated. We also measured the garbage collections. So let's look at one of the benchmark. What we did here, we varied different heap sizes starting from the minimum heap memory, minimum heap size required for that benchmark, which is represented by x. Then we extended it to 2x, 3x, and the def is the default heap size present. We saw consistent decrease in number of times the GC cycles were invoked for most of the benchmarks. And on an average, we saw reduction of 35% at the minimum heap size. We also tried to measure the performance improvement. We saw a little bit of performance or standard performance improvement for most of the benchmarks. And on an average, we saw an improvement of 6.7%. We also tried to find out the contributions that were made by different schemes. And we saw that there were noticeable contribution for most of the speculative conditions which we generated. So to summarize, we presented an approach where we enriched the static analysis with possibility of speculations at runtime. We gave a mechanism to have to incorporate these conditional static analysis results in the JIT compilers. And overall, this was one of the first approach that tries to create a balance between static analysis and speculation, harnessing best of the both worlds. You can have more details in the paper regarding what were the overheads, how do we handle different conditions in more detail with examples, and how it is different from other VMs. We try to compare with one of the VMs as well. You can find more details in the paper. Thank you.
Thank you, speaker. Any questions? While the questions are being answered, the next speaker may. Yeah.
Very interesting work. I have a question that does the speculation are always correct, or if the speculation fails, how do you handle this in this approach? For example, the optimization by JIT or something else?
Yeah, so as I mentioned, we had a fallback mechanism called as heapifications. So we have these checks present at all the places where possibly, if you are using static analysis result, the static analysis is going sound. So similarly, if you are using speculative results, those heapifications checks can still be valid, still be used as a fallback options.
Okay, thank you.
Any other questions? No? I had a very super quick question. So if you have a conditional branch, if else,
right,
and the else was executed only once,
right,
first time, and the next 1,000 times if was executed,
right,
but the global is already escaping the object,
right,
because of the else branch. So, I mean, I was just thinking about the intuition behind saying the if branch is executed most of the time, hence allocate it locally. The intuition behind that, such a check.
The intuition is that the profile data is showing us that the if branch is taking most number of the times, and we hope that in future as well it will continue to do so. That's the hope. And that's the intuition, and on that intuition we try to allocate.
All right. Maybe you can ask the question and he can answer without the slides. Yeah, go ahead.
So you said you make these checks at runtime to see if your situation is what you had in the static analysis. What are those checks typically? I'm wondering how advanced, how big,
right.
How much time consuming they are.
Yes, so those checks are at all the places where possibly an object can escape. Let's say a store statement can make an object escape. A return statement can make an object escape.
And what is it you check then?
So we try to see whether, let's say at a store statement, if you are storing into a field, if an object's field, whether that object is on heap or not.
Whether
if it is already on heap, that means that if we have done stack allocation, that's wrong.
How many cycles does it take to check that?
Sorry?
How many cycles does it take to check that?
How many cycles in terms of?
Of just checking time to check that condition.
So we try to measure the heapification checks cost. There was some overhead, but it was pretty low compared to the performance improvement which we got.
Very good. Okay, that's what matters.
Thank you.